Hello, everyone. Welcome to this revision lecture. It is going to be a very brief revision, and it is mostly going to be to refresh our memory of what we have seen in the four chapters of Chipley 8153. I will also try to give you some hints about possible exam questions, but I just want to emphasize from now that the possible exam questions that I'm going to mention, this doesn't mean that you cannot be asked for something slightly different, okay? So don't come and say, oh, Damon, you haven't mentioned this in the revision lecture. We have covered all the material during the normal lectures. Another thing that I would like to mention is that this does not include block diagrams. Okay, so I've seen various block diagrams in the module, like the open loop system, the closed loop system, the open loop estimator, the closed loop estimator. I'm not going to mention any of these things. It is in your handouts. We have extensively shown them during the lectures. Other block diagrams are the integral action, for example, and so on. I'm not going to mention these things. They are in the handouts, they are in the normal lecture notes, so I'm not going to mention them. And also, I'm not going to say anything about MATLAB. We have already uploaded a file on Canvas regarding MATLAB. Let me change my marker, it's running out. We already have uploaded a file on Canvas regarding the possible MATLAB questions. Okay, now with this in mind, let's start. Let's start with chapter 1, page number here. What have we seen in chapter 1? Effectively, in chapter 1, we refreshed our memories on ODEs. We have studied effectively first order ODEs, x dot plus kx equals u. We have also studied second order ODEs. For second order ODEs, we assume that the input here will be 0. Excuse me. Now, in order for me to solve this, I can use the classical formula, which you will be given, so you don't have to memorize this. This is going to be x naught plus the integral from 0 until t e to the kt1 u dt1. And now from here, a possible exam question here is you're given this ODE, oops, say 10, using this expression, solve it, determine the stability, and of course create a very brief graph of the response. Plenty of examples in the handouts and during the normal lectures. I don't think I need to say anything more than here. For second order system, please remember you must be able to go to the characteristic equation, hence find the eigenvalues. Say for example, x2 dots plus 3x dot minus 2x equals 0. From here, you can go to the characteristic equation, solve it, and then find the solution. Find the two solutions, x1 and x2, and then using the initial conditions, say x naught equals something, x dot naught equals something else, for you to find C1 and C2, and hence the specific solution. Just bear in mind here that, oops, sorry, missed my, it's all right. Bear in mind that in a second order case, you will have three different cases. One where R1 is different than R2, one where R1 is equal to R2 equals say to R, and one where R will be A plus minus BI. You must be able to cope with all of these three cases. Particular attention I would like to draw here when you have a complex eigenvalue. We have seen two methods effectively by taking directly as my two solutions say x1 to be equal to e to the rt. where this is complex, then in this case C1 and C2 will be complex, but when you're going to combine everything together, X must be real. I want to emphasize this, and you have seen how you can do this with several examples, Euler formulas, and so on. And the other case, where effectively x1 will be nothing more but a e to the at times cos of bt. Once again, at the end, x will be real. You can use whichever method you want, unless it is specifically mentioned in the exam question. Use, for example, complex exponentials. So very, very briefly, this is a very brief summary of our first chapter. Let's move now to chapter 2. So now, chapter 2. Chapter 2. Now, what have you seen in chapter 2? Effectively, after we had revised from chapter 1 about ODEs, in chapter 2, we moved into state space models. You must be able to understand what is a state space model. Ax plus bu, y equals c times x plus, let me add also the input-output coupling matrix. You must be able to understand, for example, that b will be m by n, u will be m by 1, and so on. So I think the important bit here in defining a state space model, apart for example, from the block diagram, is to understand what is m, n, and so on. So in this case, let's assume that I have p inputs, n for the order of your state vector, and m for the order of for the number of the inputs. The first effectively bit once we define a state space model that we have seen in this chapter is how to go from an ODE to a state space model. Again, the methodology here is more or less the same in every case. So for example, say that x dot plus 3x dot minus 2x equals, say, I don't know, 3u1 plus 5u2. So this is your ODE, which of course you couldn't solve in chapter 1. Then the methodology is always the same. Isolate the highest time derivative, create as many state variables as the highest time derivative, and then start assigning x, x dot, and so on to your state variables. Uh, Again, this is like a typical example here, which is one of my favorite questions, because then it can be combined with chapter 3 in order how to solve a state space model, and then chapter 4 of how you can control it. The second thing that you have seen is how you can go from a state space model to a transfer function. Nothing tricky here. You must be able to use this formula, g of s equals c si minus a minus 1, excuse me, times b. You must be able to derive this expression. You don't have to memorize it. So one possible exam question here is prove that the transfer function of a state space model is given by this formula. We have seen how we can do this. If you have to find the specific transfer function given CA and B, nothing really tricky here. You just have to do the multiplication. Just a friendly advice, try to do the multiplication with the most zeros. So for example, you can either start with this one or you can start with this one. So you can actually say, let's start with C Si minus A minus 1. And once you have found this, to multiply this with B, or you can say, I'm going to start by calculating this product, and then whatever I find, I will multiply it by C. If I were you, I would choose either this or this, depending on which of these matrices has more zeros and ones. To put it simply, start with the simplest possible multiplication, so that you can avoid doing some silly mistakes. Also, we have seen in this case for second order systems, A, B, C, and D to the power of minus 1. this will be 1 over the determinant of this matrix times another matrix. You must know this. Effectively, I'm going to swap the location of the first and the fourth element, D, A, and I'm going to change the signs of the second and third elements, minus B, minus C. The last bit that we have seen in chapter 2 was about controllability and observability. Um, Now, effectively, what I want you to know here are two things. One is the pretty much obvious. You must be able to calculate the controllability and observability metrics. So B, A squared, B, and so on. And through here, you must be able to find the rank of MC. If MC is a square matrix, then just play with its determinant. If it is non-zero, then the system is controllable. Similarly for MO for the observability metrics. I think this is pretty much obvious. However, one extra bit that I want you to know is what is the true meaning of controllability and observability. So for example, let's say that x1 dot equals 3x2 plus x1 and x2 dot equals, I don't know, 5x1 plus 6x2 plus u. You can have multiple u's here. I think this is pretty much trivial. I want you to be able to see this system and tell me if it is controllable, similarly if it is observable. In order to be controllable, the signal u must be able to influence both ODEs. We can see here that directly u can influence x2 dot, so it can influence the response of x2. Someone may say that since u does not appear here, the ODE for x1 is uncontrollable, but this is wrong because effectively you can indirectly influence x1 dot via x2. So this system is controllable. Now let's move on to chapter 3. So this is now page 3 in chapter 3. Okay, what have we seen in chapter 3? All that we have seen was how to solve homogeneous state space models. It's really important that if you go from an ODE to a state space model and you solve it using both the ODE and the state space model, the two solutions must be the same. It is the same system. Here it is expressed as an ODE. Here is expressed as a state space model. But not only that, in chapter 3, we have seen three different methods of how to solve ODEs. The first method was based on the eigenvalues and eigenvectors. So what is this method now about? Effectively, you use the eigenvalue equation. Through here, you're going to find R1, R2, and so on. Just before I continue, sometimes we use the expression A minus lambda I equals 0. It is the same thing, okay, just it's a different symbol for the eigenvalue. Also, some books, they use it, the eigenvector equation, sorry, the eigenvalue equation in this way, Ri minus A equals 0. Obviously, these two are the same thing. If you come here and you multiply this with minus 1, then you will get here. And the same thing, of course, for the eigenvector equation, which is going to be A minus Ri times E. It can be Ri minus A, and it can be lambda I minus A. Nevertheless, you can find R1, R2, you can find E1, E2, and then you can try and solve. You need to find now from these two x1 and x2, and then of course you need to linearly combine these just very, very briefly, we have seen here three different cases where R1 is different than R2. They're straightforward because E1 and E2 are linear independent, and hence we do just combine them. We have seen the slightly trickier case where R1 equals R2 equals R. Then in this case, I'm going to need the so-called generalized eigenvector, which can be found by Ri times E equals B. B equals E. Sorry about this. And then you can solve it as before. And the third case is when R is A plus minus BI. It is that case for ODEs where you have complex eigenvalues and and poles. I want to pause here a little bit, just highlight something because I got a few questions about this. You can keep hearing me talking about poles and eigenvalues. It is exactly the same thing. So the poles, it is exactly the same thing as the eigenvalues. Effectively, this comes from the poles. We usually use it on transfer functions and eigenvalues on state space models and ODEs, but it is the same thing. Okay, so we have open loop poles, open loop eigenvalues, closed loop poles, closed loop eigenvalues, eigenvalues of the aerodynamics, poles of the aerodynamics. It is exactly the same thing. Now, in this case, if you have complex eigenvalues, there are again two ways to do that. You can find x1 by saying that you're going to have here complex numbers in exactly the same way as before. If you do it like this and you find x1 and x2, when you're going to combine them, at the end you're going to get to a real equation, or you can say that x1 will be the real part of e to the RT times E. So these are the two different methods that we have seen back in chapter 3 of how you can tackle a system with complex eigenvalues and eigenvectors. Let's go now to the second bit. So this is page 4. In chapter 3, we have seen two more methods of how you can solve a state space model. The second method was via the fundamental solution matrix x1 and x2, where these two x1 and x2 will be found by using the eigenvalues and the eigenvectors here. Nothing really tricky. If you find the fundamental solution matrix, then you can take the product of the fundamental solution matrix with the inverse of the fundamental solution matrix evaluated at t equals 0 times x naught to find the value of x, the solution. Now, it is not assessed in your handouts, but there is a section there of how you can apply this method when the state matrix is time dependent. In this module, we do not study this. In this module, we do not have time dependent state matrices. However, I'm showing in this section of chapter 3 how you can use this method to tackle a system like this. This is not assessed. This is only for your academic curiosity. So this is another method. And then the final method was using the exponential matrix. It is possible to once again do this for all three cases, but to be fair, in these two cases, it is rather tricky. So we have only seen the exponential matrix when R1 is different than R2. So one possible here question that the students may have is, Damien, which method is the best? Well, to be honest, if I would like to summarize it here, the first method is very good because it is very simple. It is straightforward. Eigenvalues, eigenvectors, x1, x2, and then you're there. The second method, it is very good when you have to tackle systems with time-dependent components. And the third method is good. Obviously, this is not assessed in this module. So again, you have to apply it on simple systems where A, B, and C are constants. And the third one can be applied to high order systems. And also, you do not need to worry about special cases. Okay, you have repeat eigenvalues and so on. There are algorithms out there, like if you're using MATLAB, that can immediately give you the exponential metrics. Remember that MATLAB is using the command expm, and hence you can easily calculate this without having to worry about special cases. However, obviously, in this module, we have limited the choice of exam questions that you can be asked here because you have not seen high order systems, we have not seen time-dependent matrices. So one possible exam question is, you are given, for example, this system, I don't know, something like this, solve it using all three methods. All. And one of the things that I really want to see here is that if you solve it using all three methods, at the end, you get the same result. And so that was chapter 3. Let's go to our last chapter now, chapter 4. Now, this is page 5, and we are in chapter 4. Effectively, what we have seen in chapter 4, we started by talking about closed loop systems and more specifically state feedback. Again, I'm not going to mention anything about block diagrams here, open loop, closed loop, and so on. So in chapter 4, we assume that u will be minus kx. This created the closed loop system where effectively this k, which is your controlling variable, will be in your ODE. And the first and most simple method that we have seen of how to solve this is using pole placement, where effectively we target specific eigenvalues, closed loop poles or eigenvalues. It is the same thing as I have mentioned. And in this case, effectively you use the eigenvalue equation A minus BK on the closed loop matrix. You have K and R here. You're going to give the desired value for R1, R2. And for example, if you have a 2 by 2 system, and then from here you can find K1 and K2. Again, if you have a 2 by 2 system. One thing that I would like to highlight here that in theory, it is possible to make this choice. Okay, it is going to work just fine. You're going to find K1 and K2, but because your targeted eigenvalue, your target second eigenvalue is +5, this system is unstable. Okay, so if you're given something like this, I'm expecting a comment that, okay, this is K1 and K2, Damien, but I would like to flag that the second eigenvalue will make my system unstable. Then you have seen another method called LQR. That was a little bit more advanced and usually students find more challenging. There are three things that I want you to understand here and nothing more than that. The first one is not assessed, but to be honest, if you do not understand this, you cannot understand LQR, is that if you have a signal f of t, any signal, then if I want to quantify that signal, I'm going to take the squared and its integral. Okay, so by having this fellow here, I can quantify my signal f of t. So if the signal f of t is my signal u, then it is about energy. I'm going to quantify how much energy I'm going to use. If the signal f of t is x, I'm going to quantify how quick, how fast my system is going to be. The second thing that I want you to know about LQR control is that you will be given this formula R1 B transpose P. So if I give you R, B, and P, you must be able to do this simple multiplication. Once again, be a little bit clever if you will do this multiplication first or this multiplication first. One of the things that I really like in this type of questions is that after that you will find the closed loop state matrix, you will find the eigenvalues of the closed loop state matrix. Okay, and then I want you to make a comment on this. Okay, for example, say that the open loop state matrix had as an eigenvalues -1 and -2. If by using this LQR controller you go then to -0.1, -0.2, then obviously you have done something wrong here because this system is slower than this one. So the question here is, why on earth should I make my system slower? Or if you calculate something like this, say -10 and +10, then please remember in LQR control, it is not possible to have an unstable closed loop system. I need to pause here. I forgot to mention that you always check the controllability first. So if the system is controllable and you apply the LQR control, you will never get into an unstable system. And the last thing that I want you to know about LQR control, this is page 6, is, for example, something like this. Say that you have a state space model. So you will be given A and B, and you control this system using 3 different controllers. In one case, R is say 10 and Q is 10. We have seen in the class that there could be multiplied by matrices. I don't want to make it more complicated with the dimensions of R and Q. Let's say that this is a single 1 by 1 system, but the logic is the same for 2 by 2, 3 by 3, and so on. So I have 10 and 10, 1 and 1. R2, for example, can be 1. Q2 can be 10. R3 can be 10. Q3 can be 1. R4 to be 1. Q4 to be 1. So this is now 4 different LQR controllers applied on the same system. I want you to be able to tell me that this will be the fastest. Let's start with this one first, that these two will be the same. We care about the ratio of Q and R, not about their absolute values. Between these two, this will be faster and this will use less energy. Because here Q is higher than R and vice versa, comparing to this system. So this is all that I want you to know about the LQR control. Then chapter 4 was about estimators. Again, I'm not going to mention anything about block diagrams. I want you to be able to understand the difference between the open loop estimator, so E dot equals A times E, and the closed loop estimator, so E dot equals A minus GC times E, where this G is from our estimator. We can change this value. I want you to be able to understand the difference between these two and also to find the value of G given a desired closed loop pole location or eigenvalue location, but now for the aerodynamics. Okay, I want you to understand the difference between the closed loop system and the closed loop estimator, as I have said here. The important thing that I want you to understand here is the idea of where you're going to place the poles or the eigenvalues of the aerodynamics. So if say you have a second order system, so you're going to have again RE1 here, RE2 here. Then what we have said in the class that you will choose these two to be around 5 to 10 times of RX1 and RX2. Why this? Because you want to make sure that your estimator will converge, will be faster than the controller, because your controller can only operate once the estimator has done its job. Of course, someone may say here, okay, Damian, how about if I make this 1000, since effectively my estimator, or 100,000, since my estimator will be in my Simulink file. Indeed, in your Simulink file, this is going to work. For a real system, this is not going to work due to noise. And then finally, we finish chapter 4 and we finish this module talking about tracking. This is page 7. Tracking. We have seen two different methods. One is the so-called for single input, single output systems. Again, I'm not going to mention the block diagrams, you must know them, but very, very quickly, this is my desired output multiplied by K1 plus, this comes from minus Kx, and now this is my signal U. Now, you don't have to know this formula, but you must be able to derive K1 will be minus C times A minus BK minus 1 times B times to the power of minus 1. So you must be able to derive this, and of course you must be able to use it. Please remember, since we are using inverted matrices, all I can do it here is for a 2x2 system, because we do not know how to find the inverse of a 3x3 system. And the second method, multi-input, multi-output systems. Again, without making any detailed notes about the block diagram, which you must know, this is going to be your control, the desired signal. You will subtract this from the real output, an integrator. This will be K1 plus and plus. Again, this will be minus Kx, which will come from your controller. This will be now your new control signal. Apart from the block diagram, you must be able, if I give you the closed loop state matrix, so the state space model, let's ignore D, you must be able to go from this one to the so-called augmented state space model. Okay, where, for example, AA will be 0 n by p 0, sorry, this is p by p n by p minus c a, and of course you will be minus k a times x a. Now you will be given all these formulas for AA, you will be given BA and so on, and all that you have to do here is that from A, B, and C, find N, find M, find P, and put them here. So for example, if you have a 3x3 system, if you have a system with 3 outputs, 4 inputs, and 6 states, then 0 P by P will be 0 3x3. So 0 0 0 0 0 0 0 0 0. And this matrix now 0 n by p will be nothing more but 0 x by 3. Okay, so once again, given all of these matrices, you need to find n, m, and p, and hence you must be able to find these matrices. So once again, this will be given. And with this one, I have finished my brief revision for EEE 8153. If you have any questions, please let me know. Good luck with your exams. Thank you.